Hello everyone, welcome back to the lecture series on magnetism and condensed matter physics. In the previous videos, we have talked about different types of magnetic interactions which operates between magnetic moments. Now we will consider the different types of magnetic ground states which can be produced by these interactions. These different ground states includes ferromagnets, antiferromagnets, spiral and helical structures, and spin glasses. In ferromagnets, the magnetic moments are in the parallel alignment, whereas in the case of antiferromagnets, adjacent magnetic moments lie in antiparallel alignment. In case of spiral and helical structures, the direction of magnetic moments precesses around a cone or a circle, and in spin glasses, the magnetic moments lie in the frozen random arrangements. In upcoming videos, we will show how the interactions discussed in the previous lectures lead to these different ground states. So let's start with ferromagnetism. A ferromagnet has a spontaneous magnetization even in the absence of an external applied field, and ideally all the magnetic moments lie along a single unique direction. This effect is generally due to the exchange interactions which we discussed in the previous lectures. Now for a ferromagnet in an applied magnetic field B, the Hamiltonian is given by minus summation over nearest neighbor of Jij and the dot product of Si and Sj plus G mu B and then the summation of Sj dot B. Here the exchange constant for the nearest neighbor will be positive. Here the first term is the Heisenberg exchange energy and the second term is the Zeeman energy. Here for simplicity we will assume that there is no orbital angular momentum. So therefore L equal to 0 and the value of J will be equal to S. This is known as quenching of orbitals. Now let us see the Weiss's theory of ferromagnetism. The theory of ferromagnetism put forward by Weiss is centered about the following two hypotheses or assumptions. The first assumption was every ferromagnet contains domains which are spontaneously magnetized in, and in each domain there is a uniform magnetization, but the magnetization of each domain point in different directions from its neighbor. And the second assumption was the spontaneous magnetization of each domain is due to the presence of an exchange field which tends to produce a parallel alignment of the magnetic dipoles. The field is assumed to be proportional to the magnetization m of each domain. So therefore, BE is equal to lambda times m, where lambda is the Weiss's field constant. Here Weiss assumed that all magnetic moments experiences the same exchange field. So using these assumptions, Weiss assumed that the alignment of spins is due to this local molecular field, so that the exchange interaction can be replaced by an effective molecular field produced by the neighboring spins. So therefore, we are now able to treat this problem as if the system were a simple paramagnet placed in a magnetic field of B plus lambda m, so that at lower temperatures the moments can be aligned by this internal molecular field even without any applied external field. Now notice here that the alignment of the magnetic moments gives rise to an internal molecular field, and this internal molecular field causes the alignment of the magnetic spins. So therefore it is something like a chicken egg scenario, whether the alignment of spin comes first or the exchange field comes first. So therefore the Weiss's theory doesn't explain the origin and the nature of molecular field. Now let us apply the paramagnetic quantum theory. You can revise the paramagnetic quantum theory by pressing the I tab on the right corner of your screen, and you can check the derivation starting at 22 minutes. There we have seen that the magnetization is given by n g j mu b times the Brillouin function, where y was g j mu b divided by kVt. But here, in the case of ferromagnets, we will replace this b with the effective magnetic field given by b plus lambda times m. Therefore, y will become gj mu b divided by kVt times b plus lambda m. Now, the ferromagnets are characterized by the spontaneous magnetization, which is the magnetization present even in the absence of magnetic field. So therefore, we will assume the case when the external magnetic field B is 0. So in that situation, our Y will become Gj mu B lambda m divided by kVt. So therefore, rearranging will give you magnetization equal to Y kVt divided by Gj mu B times lambda. Now here in the equation 1, as the temperature will tend to 0, y will tend to infinite, and in that limit, the Brillouin function will be nearly equal to 1. Now at temperature T equal to 0, and in the absence of magnetic field, the magnetization will be maximum, and it is known as the saturation magnetization. So Ms at 0 represent the saturation magnetization, which will be equal to Ngj mu v. Now if you divide equation 3 by equation 4, you will get the ratio of spontaneous magnetization with the saturation magnetization equal to y kVt divided by Gj mu v times lambda into 1 divided by n g j mu b. And if you simplify this, you will get y kVt divided by lambda n g square j square times mu b square. Here m of t represents the spontaneous magnetization and ms at 0 represents the saturation magnetization. So if you see here, the ratio of spontaneous magnetization with saturation magnetization is a linear function of y. Also from equation number 1, the ratio of spontaneous magnetization with the saturation magnetization is equal to the Brillouin function, so that we have a system of equation given by equation 5 and equation 6, where in the both equations the ratio of magnetization is a function of y. Now the magnetization at any given temperature can be obtained by solving equation 5 and equation 6 simultaneously. Before doing so, let's see a simple example. Now let us consider we have two linear equations given by y plus 3x equal to 6 and 5y minus x equal to 10. And we have to solve here for x and y. So that we can do by the substitution or using a graphical method. In the graphical method, we plot these both equations, and the intersection of two curves will give you the solution of x and y. Now let's plot this equation 1 with red line. So at x equal to 0, the value of y will be 6. So it will be somewhere here. And when the value of x is 2, the value of y will be 0. So by connecting these 2 points, we get the curve for equation 1. Now let's try to plot equation 2 with green color. So here at x equal to 0, the value of y is 2, while at x equal to 5, the value of y will be 3. So connecting these 2 points will give you the curve for equation 2, and the intersection for these two curves will be noted, and that will be the solution for the system of equations. Here also we will apply the similar logic for solution of equation 5 and equation 6. Here first of all, let's plot equation 1. Now if you see, the right hand side is the Brillouin function, and in the theory of paramagnetism we have seen that its graph looks like this, where this curve it approaches to 1 and minus 1 at both the ends. From equation 2 you can see that the ratio of magnetization is proportional to y, so it is a linear function of y, with slope proportional to the temperature. And depending upon the temperature, we can have three cases. The first case when the slope of this equation 2 is less than the slope of the Brillouin function. That corresponds to when the temperature is below some critical temperature. The second case arises when the temperature is nearly equal to some critical temperature, and at that point the slope of Brillouin function and the slope of equation 2 matches. And in the final case, when the slope of equation 2 is greater than the slope of equation 1, in that case the temperature is above some critical value. Now let us understand these cases separately. The first case corresponds to when the temperature is below some critical temperature. And if you see here, there exist three intersections of the two plots. One at some positive value of y and another at some negative value of y, and one corresponding to y equal to 0. So therefore there exist three solutions for equation 1 and 2. First one is at y equal to 0, where the ratio of spontaneous magnetization and saturation magnetization is 0, and we will see later on that this particular point is unstable. And the other two solutions corresponds to y equal to plus minus y naught, where the ratio of magnetization is not 0 and it is corresponding to stable magnetization. So here the spontaneous magnetization is non-zero, and remember here that this is the situation when the external magnetic field is 0, and there exists a non-zero value of spontaneous magnetization even if the external magnetic field is 0. So that was the reason I was calling MT as the spontaneous magnetization. At this unstable point, any fluctuation, no matter how small, will cause the system to turn into either one of the two stable states. These two stable states are corresponding to either up or down alignment of spins. This particular temperature below which there exists spontaneous magnetization is known as Curie's temperature. Now we can also see the other two cases when the temperature is above Curie temperature. So there exists only one solution for equation 1 and 2, that is at y equal to 0, where there is no spontaneous magnetization. This particular state is known as paramagnetic state, where in the absence of any external field, the net spontaneous magnetization is 0. So therefore the spontaneous magnetization is the characteristic of ferromagnetism. Now let us find the value of the Curie temperature. The transition temperature can be calculated by equating the slope of Brillouin function with the slope of equation 2 at the origin. Now for very small values of y, the Brillouin function can be approximated as j plus 1 divided by 3j times y. So therefore the slope of Brillouin function will be j plus 1 divided by 3j, and the slope of equation 2 was kbt divided by lambda n g square j square mu b square. And here this temperature is corresponding to the transition temperature, so let's call it Tc. So rearranging will give you the transition temperature Tc as j into j plus 1 lambda n g square mu b square divided by 3 kb, and this is known as the Curie temperature. Now we can also get this value of transition temperature in terms of saturation magnetization by substituting its value equal to n g j mu b. Now for a typical ferromagnet with transition temperature is nearly equal to 1000 of Kelvin, and assuming the J value equal to half, one can calculate the value of molecular field as lambda times ms equal to 1500 Tesla, which is generally quite strong as compared to the applied external field. This is an enormous effective field, and it reflects the strength of exchange interactions. The Weiss's theory of ferromagnetism was given in the year of 1907, and at that time, the exchange interactions given by Heisenberg was not known. It was only in 1928 when the exchange interaction was proposed by Heisenberg. So at the time of Weiss, it is very difficult to explain the origin of this very strong molecular field. But later on, with the idea of exchange interactions given by Heisenberg, the molecular field was found to be a convenient fiction. If it really existed and the Heisenberg exchange didn't, the molecular field would have to be 10 raised to power 3 Tesla strong to explain the alignment of spins in the ferromagnetic material. Now the solutions of equation 1 and 2 as a function of temperature can be shown for a range of values of J. Here the spontaneous magnetization is 0 above the critical temperature or the Curie temperature, and this state is known as paramagnetic state. While below the critical temperature there exists a spontaneous magnetization and it is known as ferromagnetic state. Here the spontaneous magnetization is continuous at the Curie temperature, while the first derivative of the spontaneous magnetization is discontinuous. So this classifies as the phase transition between the non-magnetic and ferromagnetic phase in the molecular field model as the second order phase transition. The phase transition is of two types. The first one is first order phase transition, which is characterized by the fact that the first derivative of free energy is discontinuous at the transition, and it involves latent heat. For example, the transition between ice to water, it always involves the latent heat. The other type is second order phase transition, where the second order derivative of the free energy is discontinuous, and it doesn't involve any latent heat. The example of second order phase transition is ferromagnetic to paramagnetic transition. If you remember from statistical mechanics that the magnetization is proportional to the first derivative of free energy. And here the first derivative of magnetization is discontinuous. So this means that the second derivative of free energy is discontinuous. So therefore the transition from ferromagnetic phase to paramagnetic phase is a second order phase transition. Before ending this topic, let us define the order parameter. An order parameter is a quantity that quantifies the degree of order in a system, serving as a measure for the characterizing phase transition. It vanishes at the disordered phase and becomes non-zero in the ordered phase. Here you can see that the spontaneous magnetization is the order parameter for the second order phase transition seen in the ferromagnetic to paramagnetic transition. So let's end this topic here, and in the next video we will see the effect of an external magnetic field also and the magnetic susceptibility. So we will meet next time. Thank you so much for watching this video.